So good morning, calculus students. I hope you're staying safe on the slippery roads and um, thinking about calculus. So here's the video that I promised, introducing critical points or the first derivative test. So we talked briefly at the end of class what the first derivative test is. So that's an important concept, first derivative, and we'll talk about that today. There's a second derivative, in this video. Derivative test. Okay. And if we think about the first derivative test, what do you think that's going to help us find? The first derivative test helps us find something to do with slope. So it's definitely going to involve slope. And we're going to use slope, negative and positive, to help us find extrema. Extrema is just the generic word for max and mins. Max and mins. Okay. Also tied in with derivative points, or first derivative test, is critical points. Critical points are points that the x value makes the first derivative equal to 0. Let me write this out. Okay, so the x coordinate makes, make some room here. X coordinate makes the derivative 0 or undefined. That's important to understand. Okay, so that's some vocabulary stuff. So you need to know it. Of course, we already know that first derivative goes to slope, and the extrema are just max and mins. Critical points are x coordinates. Critical points, their x coordinates make the derivative 0 or undefined. Okay, and then in the second derivative test, we're actually looking for concavity, whether the graph is open up or open down. And there's things called inflection points. And so inflection points are points on the graph where the concavity changes. Okay, so that's the basic idea. They're just some little vocabulary words. And so now what we're going to do is work through this worksheet. Now, if you haven't printed off this worksheet, I would pause the video and go print it off so you can kind of follow along with me. In fact, I would even say, now that you've just heard this, this little vocabulary catch-up, you might even try just working through say the first number 1 of the video. So you would pause the video right now, work through number 1 on the worksheet, and then start the video once you've completed it. Okay, so number 1, it says use the graph of f of x shown below with domain -3 to 12 to find the following. So this, in other words, is saying it stops at -3 and stops at 12 because we have little brackets there, right? And so you're supposed to go through and find the values of x where f prime of x is equal to 0. So remember, derivative equals 0. That means that the slope is 0, which means we're looking for flat spots. So looks like there's a flat spot right there, flat spot right there, another flat spot right in there somewhere, flat spot right there. And this is actually a slight incline. It's not a flat spot. So find the values of, so where's f prime of x equal to 0? That looks like at negative 1.7, perhaps, and 2, and looks like about 4.3-ish, and looks like about 7.5. Okay. And let's erase those so they don't keep bugging us. So then the next question says find the values of x where f prime of x is undefined. So remember, undefined is either means the function is undefined there, or if there's a cusp. And so since this just ends at -3, that would be a cusp, that would be a cusp, and that little sharp point would be a cusp, and that would be a cusp. So find the values of x where f prime of x is undefined. That would be at -3, negative, looks like about 0.6, and 10, and 12. Right? Now, find the inflection points. Inflection points mean, if remember we just talked about over there, inflection points are points in the graph where the concavity changes. So if you're looking at this thing, the concavity at the beginning here is concave down, and then it stays concave down, and it comes concave up right in here somewhere. Okay, so the inflection point's got to be somewhere right about there, it looks like. It's hard to actually nail it down just by looking at it, but I would guess at about at 3. That x equals 3 would be one of them, because it's concave up for a while, and then it switches again right about there somewhere, just concave down again. So it looks like about 4.8-ish. Concave down for a little while, and then it switches to concave up again. So right about there, that'd be a 6-ish, 6.1-ish, right? So everyone see what I mean by concavity. This is concave down, concave up for a little bit there, concave down again, concave up for a little bit, all the way up to there. And then there's no concavity there because it's just flat. Okay, part D says find all the local maximums and minimums. So, and we're just going to find where they are, just giving x values. So x equals, looks like at about negative 1.7. There's a maximum. Let's erase these now. And looks like there's a, we'll break them up into max and min. So at x equals negative 1.7, looks like there's another maximum at 2. And then another maximum at 12. Okay, when we talk about maximum, we're talking about local maximum, so it doesn't have to be the highest point on the graph, it just has to be the highest point in its local neighborhood. Okay, so then we have minimums at, looks like about negative 0.6. Oh yeah, and a negative 3. So let's erase that. So negative 3, negative 0.6. No minimum there because it just keeps going down, but there would be a minimum right about there somewhere. So that would be about 7.5-ish. And I think that's it. Okay. Find all the global maximums. So global just means it's the highest point on the graph, and global minimum means the lowest point on the graph. So in this case, the global maximum would be, let's erase these now. The global maximum would be right there, which is, looks like 2, 4. And the global minimum, global min, would be right there at negative 3, negative 4. All right, so that's number 1. So again, I would suggest that if you haven't already, go try your hand at number 2 before we walk through this, and then you can come back and watch the video. So, but I'm going to go ahead now. Using the graph and your answer to the questions above, do the following. So label all the critical points on a number line. Determine the sign of f prime of x between each critical point. How does the information in this number line help you determine which critical points correspond to local maximums, local minimums? Okay, so we're going to go across here. Okay, so all of these points that make the derivative either negative or either 0 or undefined would be a and b. So I'm going to start at the left and go -3, and then -1.7, and -0.6. What's next? Looks like 2, and 4.3, and 7.5, and 10, and 12. So those are all the critical points, all the x values that make the derivative either 0 or undefined. Okay, now this is what the first derivative test looks like. You've put all the points on the number line that make derivative 0 or undefined, and then you run through and just test the slope. Is it positive or negative? So you look to the left of -3, there's nothing happening. So we put a question mark. To the right of -3, we see that it's a positive slope because it's going up, right? Once you get over -1.1, notice that it's going down now. So this is a negative slope. Once you get to the other side of -0.5, it's going up again. Positive slope. Get to that top at 2, it starts going down again. Negative slope. At 4.3, which is right about there, it keeps going down, doesn't it? At 6, wait, is 6 one? No, 6 is not one of them, sorry. There's no flat spot there. At 7.5, after 7.5, it starts going up again, so that'd be a positive slope. And after 10, it is still going up, that's a positive slope. And after 12, there's nothing happening. Okay. So now, how does this help us determine max or min? So notice that if I go nothing but up from -3, that means it must be a low spot. Here, I'm going up, and then I turn around and start going back down. That must be a maximum. Here I was going down and started going back up. That must be a minimum. So this would be max, min. This is going up, start going down, maximum, etc. So you can see by looking at this, here we find out that 4.3 is not a max or a min because it was going down and then kept going down. So if you look back up at where 4.3 was, that was right there, that somewhere in there somewhere. And it isn't a max or min. It's just a flat spot. Okay? Over here it was going down. At 7.5 it started going back up. And notice at 7.5 that's a minimum there. So we'd say a minimum. If it was going down, now it's going back up. Here it was going up and it continued going up, so that's neither a max nor a min. So that, my friends, is the first derivative test. It's coming at it from a different angle because normally we would give an equation, we'd take the derivative and find out where the derivative is negative, but here we're looking at the graph of the function and just determining the derivative by looking at the slope. Okay? But that's what it looks like. Second derivative test, same idea, but instead you're going to be looking at the second derivative. So we're looking at all the inflection points. Well, the potential inflection points. So label all the points on the number line where f prime of x is either 0 or undefined. Determine the sign of f prime of x between each mark point. How does the information, so if you look over here, where are my potential inflection points? Okay, so if you think about the second derivative, if the first derivative is undefined here, the second derivative is also going to be undefined. So at 0.6, negative 0.6, I mean. Where else did we have that? Oh yeah, -3, that was also on there. Okay. And 3, that's supposed to be negative. 3. Oh yeah, 3, 4.8, and 6. So 3, 4.8, and 6. Anything else we should be worried about? Oh yeah, 12 also, because the derivative is undefined there, so the second derivative would also be undefined there. And I think that's everything. Oh, no, 10. Derivative is undefined, so the second derivative would be undefined. Okay, so now when we talk about second derivative, we're looking at what happens to the other side here? Nothing. So that doesn't tell us anything. What happens between -3 and -0.6? Well, that's concave down, so we would get a negative there. Likewise, between -0.6 and this next one, the 4.8-ish, I have a 3 in there. Oh, yeah, right there. Between 3, it's concave down, isn't it? And then from 3 to 4.8, it's concave up, so that'd be positive. From 4.8 to 6, it's concave down again. And from 6 to 10, it's concave up again. And from 10 to 12, question mark, it's not, there's no concavity. So it would be, oh, actually it'd be 0, wouldn't it? So now if you look at this once again tells us where it's concave up and concave down. So we're saying from -3 to 3, it's concave down. Is that true? Yep, from -3 to 3, it's concave down, except for that one point right there. Okay, so that's the second derivative test. Okay, so now, number 1, it says, in each case, sketch a graph of a contingent function that with the given properties. So the idea here is, this is a picture of the first derivative test, and this is a picture of the second derivative test. And it tells me that the first derivative at -1 is 0, and the first derivative at 3 is 0. Okay, that's why we got those on there, right? In other words, it's 0 not undefined. Okay, and apparently the second derivative is 0 at 2. Okay, so what we're going to, if we look at this, using the first derivative test, we know that it was going down, and then it started going back up. So that tells me that I have a minimum at -1, comma something, right? And then here I notice it's going up, and then it started going back down. So that means I have a maximum at 3, comma something. So far so good. So that's what the first derivative test tells me. It also tells me that it's it's decreasing. The graph is decreasing from -infinity to -1 and from 3 to infinity, and it's increasing from -1 to 3. So if I'm supposed to draw a graph that looks like that, notice I don't know where the -1, 3 are, so I'll just put a little minimum at, say, -1 right about there-ish. I'll put a maximum over here somewhere. And I want to make sure that I'm decreasing, and then increasing, and then decreasing. Okay? That would fit that requirement. Now let's look at the second derivative. Second derivative tells me is there's an inflection point at 2, and it's concave up before that and concave down after that, right? So if I go over here to 2, whoops, I put that max at the wrong place, didn't I? Should have been at 3. So I'm going, come on. I'm going. So according to the second derivative, it's supposed to be concave up from -infinity to 2, which that looks pretty good. And it's supposed to be concave down from 2 to infinity. So looks like that we made it, didn't quite reflect it or switch at the right place. Maybe more like that. So I want the concave up all the way to there, and then it starts to be concave down from there. Okay, likewise here, we're looking for, oh, interesting. So negative, at 1, it's 0, the derivative is 0, but at 4, it's undefined. Which, what does that tell us that it's undefined? We think cusp. So we still are going to have a, so this is going to be going up and then down and keep going down. Okay. Okay, so let's see if we can draw that. So here's my XY axis, XY plane. And it looks like at 1, we'll just pick something up here. It's a maximum for sure up there. So it was going up. And it's supposed to be concave down until I get to 4. So here's 1, 2, 3, 4. There's 4. And let's do a little spot like this. Okay, so it's going to go down, 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 down. And there should be a sharp spot there. Okay, but notice it keeps going down. So I'm going to just keep going like that, sort of. Nope, can't go like that. Okay, so let's check and make sure. So the first derivative, it's going up until here. Looks like it went a little bit beyond that. So it's going up until here. And then it went down. Okay, so it's going up, then it went down and kept going down. And notice it's concave down from negative infinity to 4. But it's supposed to be concave up there. So we got this going the wrong direction. So we want it to be sharp here, but we want it to be concave up. So it's going to be kind of like, let's do this again. So here's my point. And again, I'm just randomly picking these points because I don't know where they actually are. If we had an actual equation, we could find out where they are. But I'm going up, 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 down, 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 down. And then here, so I somehow need to make that a sharp little turn, but it's got to switch from concave down to concave up. But keep going down. Because you can see it's increasing here, decreasing here, and still decreasing. Concave down like that, but concave up from here on. So I got to make kind of a curve that way. But that's not very sharp, but there should be a little cusp there. Drastic change in direction. Okay? This says that it's 0 at -2, 0, the slope is 0 at -2 and 2, and undefined at 0. That sounds fairly easy, but notice this is going up and then down, and then up and then down. So this is a max, and that's a max, and this is a min. So if I drew my picture, at -2, there's going to be a maximum. At +2, there's going to be a maximum. And at 0, there'll be a minimum. But that 0 is going to be sharp because it's undefined there, right? So I'm thinking of something like this. We can check and see if that's right. I'm going up, and then I'm going down, and then I'm going up, and then I'm going down. The derivative is 0 here and here. The derivative is undefined there. Perfect. Now let's look at the concavity. It says it's concave. It's undefined at 0, or it's not. There's no concavity at 0, so I got that. And it's concave down the rest of the time. Sure enough, concave down, concave down. Okay, so that's the idea of the first and second derivative tests. Now, when you get down to this is where you're actually going to use calculus and algebra to find this. So these were just the information is given to you on this little chart. So what you're going to do is take the derivative, set equals 0, and make these charts. So if we do the first one real quick, f prime of x is equal to 4x cubed plus 6x, and derivative of negative 1 is 0, 6x squared, sorry. So if we set that equal to 0, factor out an x squared, so that'd be x squared times 4x plus 6 equals 0, which means x squared equals 0, or 4x plus 6 equals 0. In this case, x would be equal to 0. In this case, x would be equal to negative 3/2. So if we're doing the first derivative test, we'd set up a little chart, and we put down 0 and negative 3/2, and then we'd check between each slot. So these are the barriers, negative 3/2 and 0 are the barriers. We're not checking there, those are the barriers. We're checking between those. So I need something on this side of negative 3/2. So if I go back up here, let's pick like negative 5. It doesn't matter, anything. And I'm going to plug it into the first derivative, which is right here. Plug negative 5 in there, and notice this is going to be, and all I care about is whether it's positive or negative. So if I plug a negative 5 in for x squared, I get positive. If I plug a negative 5 in here, I get negative. Positive times negative is negative, so it's negative right there. Let's plug in something between negative 3/2 and 0, like negative 1. If I plug negative 1 in there, I get positive. Plug a negative 1 in there, I get positive again. So that would be positive. And finally, if I plug in something over here, and you can, again, pick anything to the right of 0, so you could pick like 100 to make it clear. If I put 100 in there, I'm going to have positive. If I put 100 in there, I'm going to have positive. So it stays positive. Okay, so what did we get from the first derivative test? We found out that it's decreasing over the interval from negative infinity to negative 3/2, and it's increasing from negative 3/2 to 0 and from 0 to infinity. It's not increasing there, it's equal to 0 there. Okay, so what does that tell me? I was going down, started going up. There must be a minimum at negative 3/2. Something. What about 0? It's neither a minimum or maximum because it was going up and it kept going up. Okay, so we'll investigate what that means later. Now we're going to go back. If I want to know where the minimum is, I'm going to have to plug it into the equation. So I'm going to take 3/2 and go back up to the original equation, not the derivative, but the original equation, and I'm going to try and find out what is f of negative 3/2. So that would be negative 3/2 to the 4th power, which would be 3 to the 4th power is 81, and 2 to the 4th power is 16, plus, that's, let's see, 2 times 27 is 54 over, actually the 2 will cancel out, so that would be what? 3 to the 3rd power is 27. 2 to the 3rd power is 8, but there's a 2 cancel with it, so that'd be 4. And that would be a negative. And then finally, we got a minus 1. So that's going to be equal to 81 over 61 minus, multiply that by 4, that'd be 108 over 16. And that'd be minus 16 over 16. So we end up with, just flip those around. 81 minus 108, that'd be what? 27, negative 27, negative 30, negative 43 over 16. So I go back over here, negative 43 over 16. So I was trying to find the y coordinate of the minimum, and I found that by plugging negative 3/2 into the original equation, because this is a y value producing machine. This is a slope producing machine. So I want slope, I plug it into the derivative. When I want y's, I plug it into that. Okay. Now we're going to go ahead and take the second derivative. So let's see. 4x cubed. So the first derivative is 4x cubed plus 6x squared. So if I take the second derivative, I get 12x squared plus 12x. Set that equal to 0 and factor out a 12x. That leaves me with x plus 1. So that means x equals 0 and x equals negative 1. So we'll do the second derivative test. Put in my negative 1 and 0. If I plug something to the left of negative 1, like negative 10, that would be negative and that would be negative, so it would be positive. If I plug in something between negative 1 and 0, like negative 1/2, that would be negative and that would be positive, so I get a negative. And I plug in something bigger than 0, like 1,000, that would be positive and positive, so it would be positive. So that means I'm concave up from negative infinity to negative 1, and from 0 to infinity. And I'm concave down from negative 1 to 0. So let's try to draw, let's try to draw this thing. So we have this point, negative 3/2, negative 43 over 16, that's what? So negative 3/2 would be right here, that'd be a little over 2.5, negative 2.5, so that'd be down here somewhere. So that's a minimum. We have down here inflection points at negative 1 and 0. So it's probably good to find out where that is. If I plug 0 into the original equation, I get negative 1. So 0, negative 1 is right there. If I plug negative 1 into the original equation, I get, what, 1 minus 2 minus 3? So that would be negative 2. So negative 1, negative 2 would be right about there. Okay, so those are my inflection points. So that's where it changes concavity. So it's concave up right here, concave down right there, and then concave up again. Now let's go back up and check the slopes. Remember the slopes, I was going down and then up after 0, or down up to negative 3/2. Yep, so we're coming down like this. And then started going up until it got to 0. Went flat for a moment, but then it continued going up. So we went down, up, and the concavity was concave up, concave down, concave up. So there's a concave up, concave down, concave up. That is the first and second derivative test. So what I'd recommend for you to do is to try out these other two also. I'm going to end the video right now because it's getting kind of long, but I might post another video later with those two worked out. All right. Happy driving.